All right, working on our word problems today. Now, our log word problems end up looking a lot like our exponential word problems because we're using the same formulas. So this actually is a formula you've seen before. They just put the sub-zero in there because logs have the sub-zero, so, kind of similar notation. Well, you could use t, you could use x, y equals a times b to the x, a times b to the t. It's the same formula. So remember, if you have a percentage and it's growth, you would do 1 plus your rate. If it's decay, you would do 1 minus the rate. Still the same formula. This one over here, our continuous growth, I put that in the notes because that's the one on the Regents reference sheet. But really, you're never going to use that one really too much. The one we used for continuous growth was P times E to the RT, our PERT formula there. Sometimes they change the letters around. So instead of an R, they like to use the letter K for some reason. It's still the same formula, they're just changing around the variables. But one thing that doesn't change is E, because E is E. So again, all the same formula, these ones you've seen, these ones you've seen. So let's take a look at some word problems. So we have medical research has shown that the risk of having an accident increases exponentially as blood alcohol concentration increases. The risk, which is represented by R as a percent, is modeled by this equation here, where X is the BAC. It's the blood alcohol concentration. So what blood alcohol concentration yields a 17% risk of a car accident? So we're going to be plugging into this formula they've given us here. A lot of times with these kinds of questions, they give you the formula to use. So you don't really need to worry too much about picking which one you're going to have to use. So they told us that R is the risk as a percent. So our R is at 17%. But since they said it's the risk as a percent, we don't have to move the decimal over. We're just going to leave that one as 17. So what we're looking for in this problem is we're looking for the X. We're trying to get that X value, which is the BAC. So now we are solving an exponential equation like we were doing last class. So we want to get E by itself. So first thing I'm going to do there is I'm going to divide by my 6 to try to get E on its own. So I have 17 over 6, and again, I'm going to leave it as 17 over 6 for now, equals E to the 12.77x. So now what do we do to get the exponent down? I'm going to take the log or the ln of both sides. I had a teacher who would never let me use logs with e's, so I always have a tendency to use ln. But as we did go through last time, it really did not matter whether you use logs or ln's. You still got the same answer in the long run. I especially like the ln's with e's because, again, what does the ln of e simplify to? 1. So it just makes the equation a little easier, I think. So then what do we have to divide by? 12.77. So go ahead, type that in your calculator. Let's see what we get. Did we get that? 0.0815547279. No, I just typed in ln of 17 over 6 divided by the 12.77. Population growth. So we got Mexico City experienced continuous exponential population growth throughout the later half of the 20th century. So in 1970, the population of Mexico City was 9.4 million people. By 1990, it had grown to 20.2 million. So they first want us to find the value of k to the nearest 10,000. So the k that they're referring to is if we're using p times e to the kt. K is really your r. We're trying to find our rate here. So we have to go with the information that we have. And what do we know? Yeah, in 1970, the population was 9.4 million. So that's going to be our initial. That's where we're starting at. So our P would be the 9.4 million. The other thing we know is that by 1990, it had grown to 20.2 million. So what would I plug 20.2 in for? A. That would be our new amount, quote unquote. That's what K is. Yep, we're trying to figure out our rate, which is the letter K in this problem. T, how much time has gone by between 1970 and 1990? 20 years. So our T is going to be a 20. So those are the numbers we know. Let's go over here and plug them into our equation. So we got 20.2 equals 9.4 times e to the k times 20, or 20k, whichever way you want to write that. E is e, because it was continuous exponential growth. So that's why we knew to use this formula. So like we were doing up above, and like we were doing a couple days ago, I'm going to get e by itself. So I'm going to start off with dividing by that 9.4. Bless you. So I get 20.2 over my 9.4 equals e to the 20k. So what are we going to do to both sides? Yeah. Take the ln. But again, what happens with our ln of e? It's just 1. I really just have 20k over there on my right side. So what do we do with our 20? Divide. So they told us to find k to the nearest 10,000th. So go ahead, type that in your calculator. The ln of 20.2 over 9.4, all divided by 20. All right, so what do we get to the nearest, or 10,000th? 0, 3, 8, 2. Well, that's a mess up. 8, 2. So using the rate you found in part A, in what year will the population reach 40 million people? So still using A equals P times E to the KT. This time we want our A to be 40 million, so I'm going to put 40 in over there. Our P is still 9.4 because that's when they started looking at the population, so that's when the problem started. E is E. K is 0.0382. T is what we're looking for this time. So T stays as T. So now we'll start solving. Divide by the 9.4 again. That's going to equal e to the 0.0382t. So what do we do to both sides? ln. So the ln of 40 over 9.4 equals 0.0382t ln of e. Again, ln of e just equals 1. What do we get? So 37.91. So again, it started in what year? So 1970 plus the 37.91. 2007.91, but it would happen in the year 2007 because it's got that 0.91, so it's not quite at 2008. It happens in 2007. So looking at our next one, looking at a finance question here. So we have money in an account with compound interest grows exponentially according to that formula there. That's not a new formula. We did use that one last unit. How long will it take an initial investment of $25,000 to grow to $500,000 at 9% annual interest compounded monthly? Round to the nearest month. All right. So what is our A value for this one going to be? 500,000, because that's what we're looking for our money to grow to. We started with how much? 25,000. Then in our parentheses, we got our 1 plus. Our rate is 9%, so that's going to be 0.09. It's compounded monthly, so it's going to be over 12. And then to the 12t power. That's what we're actually trying to figure out. So to solve, what would be our first thing to do? Divide by 25,000. So what is 500,000 divided by 25,000? I heard a couple people say 20. That one I won't leave as a fraction because it actually divides nicely and gives me a nice number. It gives me 20. Inside the parentheses, combine this. 1 plus 0.09 divided by 12. What is that as a decimal? 1.0075 for the 12t. So now we have to get our 12t out of the exponent spot. We really can do either one. We can do log of both sides or we can ln both sides. But either way, you have to do one of those two things. I just picked one, log. So if I take the log of both sides, I get the log of 20 equals 12t times the log of 1.0075. So what do we divide by? 12 and the log of 0.10075. So what do we get? I got 33.41. But that's not really our answer, though. That's 33.41 years. T for this equation is always in years. They wanted to know what, though? They wanted to know to the nearest month. So what do I have to do to my number? Times it by 12. Because it was part of the formula. Multiplying by 12. Because it wanted to the nearest month. T in this equation is always years. So I have to multiply it by 12 to figure out how many months there is. So how many months do we get? Pretty sure it rounds up to 401. 401 months. It's a lot of months. Okay, so we have the accompanying table shows wind speed and the corresponding wind chill factor when the temperature is at 10 degrees Fahrenheit. So our x is our wind speed, y is our wind chill factor. Write the logarithmic regression equation for this set of data, rounding coefficients to the nearest 10,000. Okay, so to write our regression of any kind, whether it's logarithmic regression, exponential regression, quadratic regression, linear regression, in our calculator, we're going to go to the Stat button, and then we're going to go to Edit because we need to enter information into our lists. You guys remember your L1 list, your L2 lists? Yeah. So in L1, you will put the x part of your table. So 4, 5, 12, 16, 22, 31. Stat. And then go to Edit. All right, L2 would have your y column. No, I don't want plus there. 3, 1. All right. Now remember, it won't work if your lists aren't the same length. So if you accidentally missed one and one is longer than the other, you're going to get an error. So make sure all your data is typed in there correctly. So has everybody got this? Okay. So we have to do, again, a logarithmic regression. So we're going to go back to the Stat button. And we're going to go over to the right once for calc, because we're going to calculate something right now. So if we look through our little list here, we don't want 1 var or 2 var. Don't want a linear regression. Don't want quad. Don't want cubic. Don't want quartic. There's another linear. Don't want that one. ln. That's going to be our log. There isn't one that actually says log. If you look through your list, you got exponential, power regression, logistics. Don't get that confused. That's not a log regression. Logistics is something else. And then you got a sine regression. So the one we want is ln, because remember, ln is still a log. It's the log naturel, log of Napier. So we'll select that one. ln regression is the one you use for logs. So x list should say L1, y list should say L2, frequency list should be blank, so your calculator should look like mine right now. So we just keep hitting enter until we get down to calculate. And then there's our equation. So it gives you first the basic equation, y equals a plus b ln of x. So that is our basic log regression. And then they give you the values of a and b to plug in there. They told us to round to the nearest 10,000. So 4 numbers after. So our a ends up being 13.0314. Oh, 0134, sorry. I got dyslexic for a second there. And then our b value to the nearest 10,000th, it was a negative. So that's going to make it subtraction. 7.3135 ln of x. So that is our logarithmic regression. No, because remember it's base e. I'm not putting it in exponential form, I'm putting it in log form. Yeah. All right, part B. Using this equation, find the wind chill factor to the nearest degree when the wind speed is 50 miles per hour. So again, wind speed, if you look at our table, that is our x. So we're going to plug 50 in for x of our equation that we just found. So it becomes 13.0134 minus 7.3135 ln of 50. And then you just type that into your calculator. Should get a negative number. I had negative 15.59. So to the nearest degree, that'd be negative 16 degrees. So the last part, part C, based on your equation, if the wind chill factor is 0, what is the wind speed to the nearest mile per hour? So again, wind chill factor, is that X or Y? Y. Good. So we're going to put 0 in for Y. And we got to solve for X. So that means we've got to get the ln of X by itself first. So I'll subtract my 13.0134 over to the other side. So negative 13.0134 equals negative 7.3135 ln of X. Now we want to divide by that negative 7.3135. Again, with logs, I'm always striving to go for exact values, so I don't actually divide yet. Don't want to round too early. So then what do we do at this point? No, there's already an ln there. Yeah, exponential form. So our base on ln is e, and then it's to this crazy exponent here. So e to the negative 13.0134 divided by negative 7.3135 equals your x. So then go ahead and type that into your calculator. I recommend using the fraction function to help you out with that exponent. So you should have gotten 5.926 in there. So to the nearest mile per hour, 6 miles per hour.